So it gives me great pleasure to introduce Noam Greenberg, who really needs no introduction, but I'll provide one anyway. He's going to speak on the strength of the Borel Wedge comparability. Go for it, Noam.
I'd like to thank Joe, Dennis, and Peter for inviting me to do this talk. I've been lucky enough to not have much experience with giving online talks. So let's see how it goes. I'd like to talk about work that has been going on for about 2 years with Adam, Matthew, and Dan. Let's start. So what is the subject? What is the mathematical object I'm going to talk about? Wedge reducibility and wedge comparability. So what does that mean? So for now to the rest of the talk, I'm going to fix the space I'm going to work in, and that's going to be bare space. For two sets in bare space, we say that A is reducible to B if A is a continuous preimage of B. And for computability theorists, the way that you should be thinking about it is a kind of real version of many-one reducibility. This is exactly like many-one reducibility, except that instead of sets of numbers, we're talking about sets of elements of bare space, sometimes called reals. And instead of computable functions, we look at continuous functions. But just like the many-one reducibility, this is obviously transitive relation. So it's a pre-partial ordering. We say that A and B are equivalent if they're reducible to each other, and the equivalence classes are called degrees, named after Wedge degrees. These were introduced by Wedge in his thesis in the early 70s. What does comparability mean? Wedge proved that up to complements, any two Borel sets are Wedge comparable. Either, and more specifically, either A is reducible to B, or B is reducible to the complement. So in many classes, many sets of reals will not be reducible to their complement. Again, there is something quite similar happening with many-one reducible, for example, and non-computable C set is not going to be reducible to its complement. Whereas computable sets are going to be reducible to their complement. So there are sets where the set and the complement are Wedge incomparable, but that's all the incomparability you're going to get. Once we identify a set and its complement, then the Wedge degrees of Borel sets are linearly ordered. And in fact, Martin and Monk proved that they are well-founded, so they're well-ordered. And there's a very good detailed description of exactly what this kind of almost linear order, or almost well ordering looks like. There's alternating between what are known self-dual degrees, where the sets are equivalent to the complements, and non-self-dual degrees, where the sets and the complements are not equivalent. And there's a very nice characterizations of what happens at cofinality omega, what happens at cofinality omega 1. And also a calculation of the order type of various kinds of initial segments of this well ordering all the way up delta 1, 1. So for example, if you just look at the Boldface delta 0, 2 sets, then the order type is omega 1. Once you go to delta 0, 3, then there's some other ordinal associated with it. And these are, for those who know, I'm not going to talk about it, are the Veblen ordinals, but you're looking at base omega 1 exponentiation. But that's not important to this talk. How do you prove Wedge comparability? How do you prove this theorem of Wedge's from around 1972? And the answer is usually the direct approach is to use determinacy. So what does determinacy have to do with it? Well, there's a game given two sets A and B. I imagine this game in the sense of perfect information Gale-Stewart games, where the first player chooses the values of element X of bare space, and the second player, they alternate specifying values, and the second player specifies the values of element Y of bare space, and then the payoff set, the player 2 wins exactly if the relationship between X and Y and membership in A and B is the one that's expected from a reduction from A to B. So a winning strategy for player 2 gives a wage reduction of A to B. In fact, a very nice continuous function, a Lipschitz one, because they alternate specifying bit by bit. And on the other hand, a winning strategy for player 1 also gives a wage reduction in the other direction from B to the complement of A. So the axiom of determinacy implies that all sets are wage comparable up to taking complements. What's the connection between the strength of wage comparability and wage determinacy? Well, so there's some information about that. Harrington proved that pi11 determinacy is equivalent to the comparability of pi11 sets. Pi12 determinacy is equivalent to the comparability of pi12 sets. That was proved by Hjorth in '96. And going back to the game, you see one direction of these equivalences is fairly direct. The complexity of the game is directly related. The complexity of the payoff set is directly related to the complexity of the sets A and B that I'm looking at. So Borel determinacy, which is provable in ZFC, implies comparability of Borel sets under wage reducibility. What's the strength of that? Well, it's provable in ZFC, as was shown by Martin, but Friedman showed that you need quite a bit, right? To get all levels of the Borel hierarchy, you need to iterate taking the power set omega-1 many times. So you need omega-1 many uncountable cardinals. In particular, it's definitely not provable in second-order arithmetic that will be known by Z2, the system of second-order arithmetic from reverse mathematics that involves comprehension for all definable sets and induction for all definable sets. That's not strong enough to prove Borel determinacy. So if we follow these patterns, you'd expect that wage comparability of Borel sets is very strong as well. However, in 1987, Louvois and Saint-Raymond proved that in fact, second-order arithmetic is strong enough to prove the comparability of Borel sets. And the question that I'd like to investigate and talk about a little bit today is how much of second-order arithmetic do you need? And there are not many results about this. Loureiro wrote a thesis in 2015 investigating this very question, and he's looking at a variety of principles that are related and to comparability and to determinacy. So you can ask about determinacy of the wage games, you can ask about comparability using Lipschitz functions rather than arbitrary continuous functions, and he also looked at other space, at counter space as well as bare space. And he has a number of results, equivalences to some of the familiar systems of reverse mathematics. One of them is that Lipschitz comparability for clopen sets is equivalent to arithmetic transfinite recursion. And he managed to get a little bit more by using pi11 comprehension, but not a reversal to pi11 comprehension. And I'd like to say that ATR naught in some sense is the natural system to even work almost as a base system for this kind of question. I know that there's lots of interesting work. Linda told me once about it, about looking at Borel sets without ATR naught, and you have to talk about notions like determined Borel sets because deciding membership of a real in a Borel set, which is given to you automatically by ATR naught, needs to be assumed otherwise. But without going into really fine details, I'd say that the ATR naught is a system that allows you to talk about ordinals in a reasonable way, allows you to talk about Borel sets in a reasonable way, allows you to talk about trees, well-founded trees in a reasonable way. So it's good on almost essentially the right base system to work over. So the question is essentially, is it strong enough? And so I state here as a theorem, it's not quite written up, but we're fairly confident for me to state it as a theorem that arithmetical transfinite recursion is strong enough to prove Borel wage comparability. We can't get rid of some instances of pi11 induction. So I get back to the theorem at the end, but let me give you a little bit of background to our techniques. And the first part of the background is talking about essentially, well, what is effective descriptive set theory? So descriptive set theory is the branch of mathematics of set theory that deals with definable sets of reals, if you like. The Wedge reducibility is deep in that theory. Effective means that we are going to introduce computability techniques, and this is not new. This goes back to the 50s at least, where there's Addison, Mostovsky looked at the relationship between what has become known as boldface and lightface classes. So lightface means effective, and boldface means relativized to all oracles, essentially. So these are equivalences that were definitely noted by Addison. So for example, I can talk about effectively open subsets of bare space, those that are generated by CE sets of finite strings, of natural numbers. And this can be relativized to any oracle. I can talk basically by using CE relative to an oracle. A set is open if and only if it is effective relative to some oracle, because every open set is generated by some set of strings, and some, that set of strings has a Turing degree. That Turing degree can enumerate it. A function, exactly the same way, a function is continuous if and only if it is computable relative to some oracle. That means that to compute a function, all I need is the Turing functionals that we know and love, but we might need an extra parameter there to compute, and that's what continuous functions are on their space. And a set is Borel if and only if it is hyperarithmetic in some oracle, and so on. So we can use this and use reasoning about effective objects to prove general theorems of descriptive set theory that do not mention computability. There's an example that I really like, and there's tons of them. So this is an old theorem of Rosin and Suslin that says, suppose that you've got a Borel set, suppose that you've got a continuous function. And restricted to that Borel set, the continuous function f is injective one-to-one. Then the image is Borel. And in general, this is, you need f to be one-to-one, because otherwise, as images of continuous functions, you can get all analytic sets, all boldface sigma 1-1 sets as images. So this says that in this instance, the kind of images you get won't be as complicated as you could imagine them to be. And there's a classical proof to that, but here's an effective proof of that. So after everything relativizes, as we know. So I'm going to just drop the oracle and assume that f is computable and that b is lightface delta 1-1. In other words, a hyperarithmetic set of reals. Take any point in B, call it x, and let y be the image f of x. Here I have a predicate with y as a parameter and x as a variable that is delta 1-1. The unknown is in the set B and y is its f image. X is the unique solution to this predicate, which means that it is delta 1y singleton relative to y, and delta 1-1 singletons are precisely the hyperarithmetic sets. So relativized to y, this means that x is delta 1-1 in y, or x is hyperarithmetically reducible to y. So now, looking at any point y and asking, what is the complexity of asking, are you in the image of B under f? First of all, you can just write the definition of image of a function, and this is a sigma 1-1 definition of the image of B under f. But also, you can replace the existential quantifier that ranges over all reals by an existential quantifier that ranges only over the reals delta 1-1 in y, or hyperarithmetically reducible to y. And Spector and Gandhi showed that this kind of quantifier is in fact pi 1-1. So what I'm highlighting now is a pi 1-1 definition of f of b, and therefore it is both pi 1-1 and sigma 1-1, hence it is delta 1-1. And Kleene proved the effective version of the Suslin theorem that says that hyperarithmetic is Borel, hyperarithmetic is lightface delta 1-1, equivalently analytic, co-analytic is Borel. And there's tons of other examples from along the years of applying effective techniques in descriptive set theory, from kinds of things like that I just talked about, effective proofs of known theorems, all the way up to really sophisticated techniques in computability that really seem to be the only reasonable way in several situations to prove a theorem that doesn't mention computability at all, like Louveau doing using Louveau separation, which is an effective theorem to solve a question about sections of Borel sets that doesn't mention computability. The same way with dichotomy, what is known as the E0 dichotomy or the Grimm-Efros dichotomy for Borel equivalence relations is proved using effective means, and similarly what is known as G0 dichotomy for Borel chromatic numbers of Borel graphs is also used by similar effective techniques, using effective ideas, and also again the Harrington topology, which is based on lightface sigma 1 sets, and so it essentially relies on effective classes. Let me look in more detail into one of those relationships between effective and non-effective aspects of descriptive set theory. Here's a theorem that goes back to Korotowski that characterizes what boldface delta 0 alpha means. Now you'll see that in a variety of my talk, because I thought I should be precise, I'm using 1 plus alpha rather than alpha, because there's a mismatch at the finite level of the hierarchy. For infinite levels, of course, 1 plus alpha is alpha. So don't worry too much about that. Think about delta 0 alpha, alpha is infinite. So what does it mean for a set to be delta 0 alpha boldface? And that is in the Borel hierarchy. If and only if it is reducible to simple sets, essentially a clopen set, restricted modulo a closed set. By what kind of reduction? Well, not a continuous reduction, but a bare class alpha reduction. All right, so bare class alpha means you iterate alpha times the process of taking pointwise limits starting from continuous functions. Equivalently, the pullback of open sets is sigma alpha, 1 plus alpha. So these kinds of functions are the functions that allow us to reduce complicated sets to relatively simple sets, delta alpha to clopen. What's the lightface version of that? The lightface class, delta 0 alpha, is the class of things that are reducible to effectively clopen sets, delta 0 sets, under the alpha jump, the alpha jump operation, right? So the alpha means take the Turing jump and iterate it alpha many times in the sense of cleaning, inspector. Right, so in some sense, when I look at effective classes, there is a universal bare class alpha function, which is the alpha Turing jump. How do I use it? So here's a proposition, a fact about Borel sets that is used extensively in descriptive set theory. If A is Borel, then I can enrich the topology, but not too much. Not too much means it still remains Polish. It still comes from a complete metric on the space. I don't add any kind of Borel sets, but the particular set I started with can be made clopen, can be made simple in some sense. The serious restriction here really is this making it Polish, because you can take all points, all closed sets. If I can make all closed sets clopen, but that would involve making every singleton clopen, so I have a non-separable space. So the tension here is between simplifying a set, but keeping the topology not too rich so that it is still Polish. And there is a variety of proofs for that, but and there's a very nice paper by Gregoriades that I saw recently that talks about, in more detail about just how effective the theorem is. But it is effective in the sense that you can just look at the alpha jump and pull back the topology from the image. Yeah, I'll get back to that in a second. But now I want to look at what are known as true stages. So what's that? So now we're back to a completely different area of computability, computable model theory or computable structure theory. True stages are a technique that allows us to do iterated priority arguments. This originated in computable model theory to prove theorems of the form. Like this is just one example of a form that of a theorem that seems to need an iterated priority argument. So you know how when we do priority arguments, we think of finite injury arguments as those that happen with the level 0 jump, and then most like infinite injury arguments like minimal pair or something like that are considered to happen at level 0 double, and then there's more complicated arguments starting with Lachlan that talk about zero triple arguments, and if they're done as a tree construction, that usually means that that 0 jump or 0 double or 0 triple is the oracle that is required to answer the question, how are all the requirements met, and how complicated is it to compute the true path on the tree of strategies? When we want to prove theorems like this, we need 0 to the alpha arguments for computable ordinals alpha, well beyond 3 or 4, 1 or 2 or 3. So, and the idea here is, how would I prove it? I'm given an object which is computable by some iterate of the Turing jump, and you need 2 alpha plus 1 many jumps to compute this linear ordering L, and I want to build a computable object. Well, how do I do this? I basically need to guess as to what L is by approximating this oracle, and build something that eventually will have the right shape, even though I'm not allowed to take back things that I've done when I've guessed incorrectly. I need to somehow manage to find a way to recover from my mistakes. And there's a variety of technical frameworks that allow us to do this. The one that is, I think, now most popular is the one presented in the book by Ash and Knight, which uses Ash's eta systems and the meta theorem that is used to do these priority arguments. There are other methods that I won't talk about. Harrington had his worker arguments that were recently used by Owe and Andrews and Julia Knight to construct strongly minimal theories. And then there's Lemp-Lerman trees of strategies that are used to construct particular kind of embeddings of jump lattices into the Turing degrees. And the true stages is one of those techniques. It is, in some sense, a dynamic presentation of Ash's eta systems, except that in some sense, it's a bit more versatile even than Ash's. And this was introduced by Antonio Montalban, building on an idea of Lachlan. So what was Lachlan's idea? Suppose that alpha equals 1. So I now want to somehow approximate 0 jump within my working computably, working effectively. So take any CE set, then we will apply this. We'll apply this, what's happened here, to the CE set A equals 0 jump. Take any CE set, and so it almost by definition, it has a computable enumeration. So I imagine an effective process that lists the elements of A not necessarily in order, and let's call NS really the number that enters A at stages. And we have the notion of a non-deficiency stage means that at a non-deficiency stage, a number goes in and no smaller number will ever go in later. And there's infinitely many such stages, because just think for any stage, the next non-deficiency stage, you just think what are all the numbers that enter later, take the smallest one, go to the stage in which it enters. That's a non-deficiency stage. And the set of deficiencies, having infinitely many non-deficiency stages suffices to compute the set. So the set of deficiency stages, the complement is simple. This shows that every non-zero C degree contains a simple set. And Machland's idea was, within the situation, suppose that at every stage S, I can think of A sub S, the set of collection of numbers that were enumerated into A up to stage S, as a kind of guess. This is what I think A is with the information that I have at stage S. Machland said, well, if we are a bit more humble, and instead of guessing all of AS, you just trim it at the number that just entered, saying, I think that the values of A up to NS is what I see now, and I make no commitment about what happens later. Well, then at non-deficiency stages, I will be completely right. So if I just restrict my claims about what zero jump is, I can get a notion of many stages at which I will completely right, and because these numbers eventually go to infinity, as the stages get later and later, I will claim more and more, and each one of those true stages, or one true stages, I will be correct, right? So stage is one true if my restricted guess at stage S as to what zero jump is actually completely correct. And then I can apply this to do finite injury priority arguments. So suppose I want to do some kind of construction. I'm building a computable object, for example, an enumeration of a CE set or a computable structure, and I want to guess at some delta T information, like that linear ordering, complicated linear ordering that I want to guess at in order to build something computable related to it. So we have some delta 2 questions to ask, and at each stage we've got an approximation as to what zero jump is, and it might have enough information to answer these questions or not. But of course, working computably, we do not know what stages are one true. The collection of one true stages is Turing equivalent to zero jump. But at any given stage T, I can look back and think at every previous stage, what was my guess back at stage S? And what do I think about it right now at stage T, right? So it's possible that, we're looking back at stage S, and stage S made some claim about zero jump, and later I saw that a smaller number went into zero jump. Then at stage T, I already know that S is not one true, right? So if S is not one true, this will eventually be revealed. If S is one true, then every future stage will think that S is one true. Think that I have no information proving yet that S is not one true. So as far as I can think from the point of view of stage T, S still appears to be one true. And moreover, if T is a one true stage, then its opinions about the previous stages is also going to be completely correct. So what makes essentially these style of constructions work is that this relation S appears one true at stage T, which was denoted by Antonio like this, is a computable relation for finite stages S and T. And so at every stage T, I look back at the construction that I've done so far. Each stage was relied on some set of assumptions. At each stage T, I have an opinion about which of those assumptions were justified or not. And that will inform me how to continue the construction, and to tell me what were stages in which I did things that are now seen to be mistakes, and what stages I've done things that still appear to be based on the correct assumptions, and therefore those are the kinds of actions that I want to preserve and build on. And Antonio's idea was that this can be iterated up the computable ordinals. All right, so if I know what one true is, one computing zero jump correctly, what is two true? Two true will be a system of stages which compute zero double jump correctly. And this can be defined inductively. What does it mean to be two true? Well, first of all, it has to be one true, because how do we compute zero double? Well, what is zero double? Zero double is zero jump relative to zero jump, right? So how do I approximate zero double? Well, I approximate zero jump by seeing the enumeration of zero jump up to some point. Restricted myself to a piece of oracle, my current guess as to what zero jump is, and then using that piece of oracle as an oracle in an enumeration process that with oracle zero jump will give me zero double, right? So a stage is two true. What does that mean? That means it is one true relative to the one true stages. It has to be one true, but also when I just look at the one true stages, giving me the correct, more and more of the correct zero jump, and looking at the enumeration of zero double that is done by these oracles, now I am a non-deficiency stage. That is two true, and the relation appears two true at stage t is defined analogously. And this can be iterated up the finite ordinals. And then the question is, what is lambda true for lambda limit? What is omega true, for example? Well, what is 0 to the omega? 0 to the omega is just the join of the 0 to the n's, the finite iterates of the Turing jump. So lambda true really should be, omega true should be n true for every n. And so, and this is true for any limit ordinal. And the main question of setting this up when we are dealing with transfinite ordinal, with infinite ordinals, is why on earth would there be any lambda true stages? Why are there omega true stages? And it takes a little bit of work. There's some kind of diagonal intersection argument that is involved. Antonio did it originally one way. Dan and I managed to come up with a different way to set this up. But there's some fiddling involved, but you can make it work. And there's an important technical device there that essentially you can replace the jump by the sequence of beta true stages. It has the same Turing degree, and it behaves in some sense topologically nicer because it lives in bare space rather than in Cantor space. Okay. Right. Now for descriptive set theory, I want to not start with 0. I want to start with any real x and to iterate its jumps and to do it in a uniform way, uniform in x. Right. So for every x separately, I can do exactly what I said. Instead of the empty set, start with x and just relativize everything in what we've done to the oracle x. What does it mean to be alpha true or appear alpha true at a later stage when all the computations and all the enumeration processes involve x as an oracle? So instead of 0 jump, 0 double, 0 triple, I'm looking at x jump, x double, x triple, and so on. But you can also make it so that the relation appears true at stage t depends only on the oracle up to t. This is nothing special. This is the standard arguments that, you know, before stage s, no number smaller than s are enumerated into kind of any kind of C set and so on. So what that means is that now, if this only depends on x up to t, then I can forget about the stages and just look at the relations on strings, right? So sigma appears alpha true at stage tau if tau is an initial segment of an oracle, sigma is an initial segment of tau, and for any oracle x extending tau, the length of sigma appears true at the length of tau. From now on, we won't need actually the definition of which I didn't give in detail, but just these kind of properties of these systems of relations, right? So tau is a beta true extension of sigma, or sigma more precisely, sigma appears beta true to string tau, is a system of relations that have all of these nice properties. Starting with 0, this is just extensions on strings. The relations are nested. It's harder and harder to become beta true the bigger that beta is. They are continuous. Just like for numbers, for limit lambda, Lambda true is the same as beta true for all beta strictly smaller than lambda. And topologically, deciding whether sigma is beta true in X, right? In other words, for oracle X, the length of sigma is a beta true stage. This is a delta zero beta, technically 1 plus beta predicate, and this is uniform in all possible ways. And moreover, when we just restrict ourselves to finite strings and look at these relations appear beta true at a later string, this is a nice structure. It's computable uniformly, and the ordering is a tree, not in a tree in the sense of actual subtree of bare space, but a tree in the sense of graph theory, that this relation is a partial ordering, which is a tree. So the children of some sigma there could be infinitely many children, all strings. The next strings that think that beta is that sigma is beta true, there will be the immediate children of sigma on the tree. There will all be extensions of sigma, but they won't necessarily be 1-bit extensions. There could be longer and longer and longer extensions, and they'll all be at the next level above sigma. But nonetheless, it is a computable tree. And moreover, I can give a complete characterization of its path. Its paths essentially are the beta jumps of all reals. So for every real X, remember real I mean element of bare space, each path in the zero tree corresponds to a path in the beta tree, which is essentially its beta jump, which is in this context formalized as the collection of all initial segments which appear true at X. Remember what this means, going back to the stages idea, is that this is the collection of all initial segments whose length is beta true when I use X as an oracle. So there's a bijection between the parts of the tree and reals, and essentially the parts of the tree are the jumps of X. So this map really is the Kuratowski's beta, bare class beta function, and universal in its class. And going back to Kuratowski and our characterization of delta sets as the jump, this is yet another way of formalizing the idea that a set is delta beta if and only if its jump lies in some clopen set, effectively clopen set. This says just on the sigma side, what does it mean to be sigma beta? That means that your jump is in some effectively open set, which in this context, formalized in this way, just means that effectively open is determined by finite set of strings. I'm looking for strings that think that you're in the open set and appear and are true for that real X. Right. So this is just another way of saying this, but using a particular technical device that has extra nice properties. Okay, so here's some simple applications. Take a computable ordinal. Let's go back first to the change of topology argument that I talked about some minutes ago, about how you can take a Borel set and change it to be clopen by enriching the topology. And we said basically pull back, the proof is pull back under the jump. Right? Why is this Polish? Because I'm looking at the collection of jumps as a closed set in bare space, and I'm checking the subspace topology, and the subspace topology on a closed set is Polish. To be specifically precise, I can metrize this by the following metric. Right? If I don't take any jumps, what's the distance between X and Y? It's 2 to the minus sigma, where sigma is the longest initial segment. If you want the beta topology, then just don't look at any initial segment, look at the longest initial segment that they both think is beta true. So basically, this is the metric that is given by taking X and Y and looking at the corresponding paths on the tree J beta and looking at the distance on that determined by that tree. So this is the same topology as the beta jump topology. Here's another application. the Hausdorff-Kołakowski's theorem. So what does the Hausdorff-Kołakowski theorem say? It's a characterization of, to begin with, delta 2, but then higher up, all delta successor classes. It says that every set in level delta xi plus 1 lies in the Hausdorff difference hierarchy. What's the Hausdorff difference hierarchy? D2 is the difference of two sets. So D2 sigma 1 is takes an open set and subtract an open set. D3 is take an open set, subtract an open set, but then add an open subset, and so on. Formally, this is the definition. I don't want you to think too much about this definition, because the way to think about it is effectively, right? So let's just take here xi equals 1. What does delta 2 mean? So what does it mean for a set of reals to be effectively delta 2? Well, we have the limit lemma, and the limit lemma works uniformly. That means that for every finite string, I have a guess, yes, no, 0, 1. And for every path, I take the limit that stabilizes on initial segments of every real, and the limit is the result membership of X in A or not. What does it mean to be at the 8th level of the Hausdorff hierarchy, now with lightface sigma 0, 1? So this is effectively open. So the sets in the sequence are uniformly effectively open. What does that mean? That means that the membership in A is eta CE, uniformly in X. So remember, eta CE means I have a guessing procedure, which is just like the limit lemma, except that there's on the side, I'm specifying an ordinal below eta. And if I want to change my mind about my guess, then this ordinal has to go down. So in some sense, the ordinal gives me a bound on the number of times I'm going to change my mind, where of course this could be infinite, so it's not strictly speaking the number of times. To be thinking that the longer the ordinal, the more space I have to change my mind about membership, right? And this works for sets of reals the same way that it works for sets of numbers in a completely uniform and Lipschitz way. So the same way that I characterize delta 2, what does eta CE means for sets of reals? That means that I have this kind of guessing procedure, which is a delta 2 guessing procedure. But associated with that, I also have a function into the ordinal, and if I'm looking at the sigma side, this is eta plus 1. So I'm talking about Ershov's definition of his hierarchy sigma minus 1. R is in some sense a rank. It tells me how much space do I have left to change my mind. And rank 0 means no more mind changes. So if the ranks cannot go up as I extend my oracles. If I want to change my mind, then the rank has to go down. And because I'm working on the sigma side, I always start with the answer no. If I want to look at the complements, then I will start with yes. If I'm looking at the ambiguous class delta of that, which we call eta, then that just means that you have to start always with an oracle below, with some value below eta. Okay, and so the effect of Hausdorff-Kołakowski, which was noted by Louvois and Saint-Raymond in the 1988 paper, but also by Selivanov later and by Pauli later, is that this works effectively. Right. So how do we do it? Well, there's really essentially one proof, and that proof is effective. But true stages, in some sense, true stages will be used to get this up the hierarchy. For just for delta 0, 2, I don't need true stages. Just quickly the idea, right? I'm given a delta 2 approximation to a set in this sense, a computable guessing procedure for the set A, and I want to associate a ranking function to that very approximation. What is the rank? And I basically define the minimal rank that works. The rank is sigma if no future mind changes. The rank is 1 if I'm allowed a single mind change, but after that, no more mind changes, and so on. This is the formal definition for the ranks also in the transfinite. And to define rank gamma, I need gamma many jumps. And the whole point is that this will have to stop at some ordinal, the empty string will eventually be ranked, because if not, if it's ill-founded, then I will be able to construct a path on which the guessing process does not converge, contrary to the assumption that I started with the guessing process for a genuinely delta 2 set. And the whole process is hyperarithmetical, so the rank of the empty string will be a computable ordinal. And then that should be computable psi. For psi bigger than 1, this works in exactly the same way. And you can just repeat the previous proof, but replace string extension by appears psi true to tau. Just do the same proof, except that instead of taking the tree omega less than omega, replace it by the tree G beta and repeat the proof. And this is a kind of like a way that I like to present the pullback. Boldface, the variety of ways to do this, but perhaps the most straightforward way is to do the change of topology argument and reduce it back to the case delta 0, 2. Using jumps, you can just do it directly. I'm running out of time, I think, right? So let me just say, I'll skip this. I'll just say quickly that Wedge, in his thesis, gave an analysis of delta 0 alpha sets for limit alpha, and it works using the operation of partitioned union. And he used essentially a change of topology. He used Korotowski's characterization of delta alpha, and we can use the same thing to prove the effective version of that, relying on the particularly nice property of lambda true for limit lambda, where at level n of the tree, I don't need to look at all of 0 lambda. I can go to some lambda n. Lambda n's are increasing in cofinal in lambda. And this works very nicely for Wedge's theorem, but I won't talk about that. Going back to Wedge comparability, all of the applications that I've given you so far, essentially, I don't think that they're particularly novel in the sense that they are just a way of using jumps in a kind of orderly fashion. What the true stages are really good for is for doing priority arguments up alpha. What we've done so far for Wedge's theorem and Hausdorff-Korotowski, it isn't really a priority argument. But priority arguments come in to prove our theorem. So how do you prove that Borel Wedge comparability? Usually it goes the other way around. First you prove comparability using determinacy, and then various kinds of authors give various kinds of descriptions of all possible Borel Wedge classes. And of course we can't use determinacy because determinacy is not provable in second order arithmetic. And so Louvois and Saint-Raymond's original proof is the one that we need to follow. And what they do is they first define descriptions of all Wedge classes, show that they have universal sets, then show that the classes with descriptions, we haven't yet proved that all the classes have descriptions. Show that the described classes are almost linear ordered and well-founded, and then carefully understand the delta part of every described class to prove that they are all, that all classes are described. And in second order arithmetic, we need to do everything effectively. Here's I don't know what, I should probably stop. But just briefly to finish, there's a separation theorem that is a generalization of the comparability that when applied to a universal set gives you comparability. And to prove that theorem, Louvois and Saint-Raymond use some kind of notion of unraveling games. And Andrew Marks in his talk on CTA a year ago said that in some sense they invented true stages. I'm not sure that that's completely fair in the sense that their system is really geared towards just towards these unraveling games, whereas the alpha true stages are so versatile that they can be employed to a variety of tasks. but also I think that making the proof using true stages is much clearer than what they've done. And so basically, the arguments for this closed game come from an iterated priority argument. And ATR naught is used in many places, but most specifically, we're using the fact that it proves closed determinacy. Okay, so I should stop here. Sorry about rushing towards the end. This is my inexperience at online talks. Thank you.
Thank you, Noam. Are there questions? We should actually, let's thank Noam.
You should have probably made it clear that you actually had till the end of the hour. Well, end of the half hour.
Sorry, I thought it was a 15-minute thing.
Well, I failed.
I mean, if you want to say a few more words.
So what did you say too quickly that you would like to articulate now?
I don't know, I skipped so much. But let's look at the more slowly, just at the last slides maybe. All right, so I described this idea. This is all very informal, about a process of how do we prove Wedge comparability in second order arithmetic, which is essentially going roundabout in the usual way. And the main part of that is showing that two described classes are comparable. So described classes are things like the 8th level of the Hausdorff difference hierarchy over sigma psi, or take open partition of the space and make each piece in a described class, and that's a new description. So you can think of descriptions as kind of like well-tagged, well-founded trees that give you decision procedures as to membership of the class, and these decision procedures can be fairly complicated because there's lots of classes. But so what we take is two described classes, equivalently universal sets for these described classes, and show that those sets are comparable, and that's the main step of the argument. And in fact, that comes from a slightly more general theorem, the separation theorem that is presented here, which says that suppose that on one side I have a set A and its complement that I want to reduce to B. And instead of B and its complement, I've got two disjoint sets, and they don't have to be Borel, they can be sigma 1, 1. Then either there is a reduction of a continuous function that takes A into B0 and the complement A into B1. So it's kind of like a strong reduction, completely separating A and A complement by B0, B1. Or if that cannot be done, then I can find a separator of B0 from B1, which is in the dual class of gamma. In the gamma check is the class of complements, right? So sigma check is pi, and so on. So if you take a universal set for gamma and take B to be any Borel set and applies the theorem, then either the first part will give you a Wedge reduction of A to B, or a separator for set and complement just has to be the set. So that tells us that B is in the dual, the B complement is in gamma. And because A was universal, A complement is universal for the complement of gamma, so B is reducible to the complement of A. Right. So the question is how to prove this theorem. And you can write down again, but if these sets, A and B0 and B1 are complicated and B0 and B1 are not even Borel, then it's not clear what the complexity of the game. So the idea is to replace the game by a closed game, which is like a more complicated game with simpler payoff sets, in particular a closed payoff set. And this is what Louvain and Salomon do, and that's in some sense the most mysterious part about the series of papers. It's quite a hard argument that and so our ideas are that this could be simplified quite significantly and shown to be work in ATR naught. But the general idea is that instead of just playing reals in A and B0, B1, player one plays a real in which will have to be an A or its complement. And then player 2, it attempts to play a real Y in either B0 or B1, and also a witness to membership in the sigma 1, 1 set. But you're playing bits, but the final thing that you're reading is not all the bits that you played, because as player 2 is playing, he's trying to guess, given the very finite pieces of X that is seen, whether X is an A or an A complement. And if A is, say, sigma psi, it needs psi many jumps to do that. And so this is the strategy, the game for 2, in some sense, is the priority argument that says, you know, which should I believe? X is an A, X is an A complement. Well, that depends on X to the jump psi. Well, what do I currently think? What does my current approximation to X say about X to that iteration of the jump? And therefore, what does it say? What is my current guess? And so in our version of the game, player 2 plays a sequence of bits for its Y, but the actual bits that count are the ones that he played in the psi-true stages. And that's how the priority argument works. Right, so that's the elaboration.
Thank you. Other questions? Joe, in particular?
No, I just wanted to hear that.
I have a question on the unraveling. I remember years ago, Leo Harrington had asked about you know, what's the sort of ultimate of the workers' arguments is what he was thinking of. But my thought was it should be Borel's compactness or Borel's causal compactness, and this is doing something like that. I mean, you want to get to pi 1 1 sigma 1 1 things because you can do in some uniform way the alpha levels. There are a number of specific results that work this way. You prove some specific result for various computable ordinals alpha, and then you get by Borel's compactness the fact that you can do something uniform for all. You sort of get a limit. Is there anything like that in this unraveling the games?
Not that I know of, because here in this case it's just used to prove things about Borel sets, not about sigma 1 1 sets.
Yeah.
And in fact, you know, by Harrington's argument, you can't use this to prove comparability of sigma 1 1 sets, because that actually requires sharps. That's not provable in ZFC. Mm-hmm. So it won't be something straightforward like that. So because we are just looking at Borel sets, we're just looking at the countable ordinals, and the effective version, you're just looking at the computable ordinals and not carrying it forward. There's different work where you know, more towards the computable model theory side, where these true stages are used in a kind of overspill, conjoined with an overspill argument. So you're going in all computable ordinals and beyond. And so that's another way of looking at this kind of compactness.
Mm-hmm. Mm-hmm. Thank you. It was a lovely talk.
Oh, thank you.
More questions? If not, let's thank the speaker again. Thank you. Great talk, Noam.
Yes.